right, welcome to the second of our lecture series for Saturday Morning Physics for Everyone for fall 2019. So I'm Yoni Khan, I'm a new professor. I do high energy particle physics, I look for dark matter, but I've been very excited to see a topic like this because I really don't know much about the physics of baseball, and I'm super excited to learn a lot more. So let me just give you a little bit about our speaker today. So we have Professor Alan Nathan, who's a professor emeritus in the department here. He got his PhD in 1975, came here in 1977, I think has been here ever since. So his research now is the physics of baseball, and in particular, the dynamics of collisions between the ball and the bat, and the aerodynamics of a baseball in flight. So again, basically all I know about this is that momentum is conserved when you hit the ball with a bat, and there's no air resistance when the ball travels through the air, so I'm sure he'll tell me that all of the ways in which those assumptions that you learn in freshman physics are wrong. In important ways. And so I guess, so one thing to note is that Professor Nathan serves on the editorial board of the journal Sports Engineering, and one of his papers on the performance of baseball bats actually serves as a basis for efforts to regulate the performance of bats that aren't made out of wood. So sometimes doing research in physics can have extremely useful practical applications. So Professor Nathan, I'll let you take it away from here.
Okay, well, thanks for the introduction. Thanks to all of you for coming. Special thanks to Patrick and Erica for helping to organize it, and especially Erica for setting up this little demo that I'm going to show you. And thanks to my friend Dan here for this very nice picture. Now, I actually prepared this talk a bit over a week ago, and last night at 2 a.m. I woke up and realized that today's a very, very important date, and I needed to modify my slides to reflect that important date. And the date is this, 9/28/1960. This is Ted Williams in his last ball game, in his last plate appearance, he hit a home run. So today is the 59th anniversary of that event. Actually, I have this picture, an 11/16 version of that picture, sitting on my wall at home, autographed by the man himself. Okay, so by the way, you know his number was 9. Okay, and so I will steal that number, even though it's been retired for many years. Okay, so this is how I got started doing this. I read this book. And this is now the third and almost surely the final edition of this book. Bob Adair has a background very similar to my own, although he's a lot older than me. I think he's 95 years old now. And there's an interesting story about how he got involved writing this book. But this is a wonderful, wonderful book because you can get a lot out of this book, whether you're a physicist or whether you're a baseball enthusiast or somewhere in between. It's very, very readable. There's no formulas in it really at all. And it's a really great example of how a physicist communicates to sort of the general public, non-experts on science. So there's some very interesting quotes, either from this book or from talks I've heard him give. The physics of baseball ain't rocket science, it's much harder. So you know, when you do textbook physics, you know, you set up certain situations and everything is quite nicely defined, okay? The laws of physics apply and everything. But in baseball, it's the physics of everyday life, and things aren't quite so obvious, okay? So you can't, there are lots of problems that you simply can't solve from first principles, so you have to create a model. And you constrain that model with the laws of physics, and then you do experiments to help further constrain things that you don't really know from first principles. And of course, the big laboratory for experiments is the actual game itself. So the other nice quote from Bob Adair is, the physicist model of the game must fit the game, of course. So, you know, and that's why the game itself it provides such important information about things that we really don't know from first principles. Another good reference is my website. Here's Ted again, okay? All right, so here's an outline of what I'm going to talk about. They're really sort of two generic topics, the ball-bat collision and the spin of the batted ball. I'll cover that third. The flight of the baseball is the other major topic that I'll talk about. And then touching all the bases. So putting it all together, and I want to talk towards the end of my talk about the recent surge in home runs in Major League Baseball and how we could come to understand about that based on all this stuff above here. Now, before going on, I have a personal journey story to tell. The very first time I talked about the physics of baseball was here in this room as part of this series back in 1997. And there's the topic, when Ash meets Cowhide, the physics of baseball. And so the story is this. It was, my number had come up, okay, it's your turn to give one of these talks. What are you gonna talk about? Mostly people are talking about their own research. My research at the time was experimental nuclear physics. But this book here was something that I had had on my shelf. This is the first edition of the book. Came out in 1990. I bought it in 1990 or 91, and now it's 97. I never really had opened the book, and I thought, all right, I'm going to agree to give a talk on the physics of baseball, and that will force me to read the book and learn something, and I'll give a talk on it, one and done. I'll move on to my normal everyday life. However, as it turned out, there was a News Gazette reporter in the audience, and he interviewed me afterwards. He wrote it up in the paper the next day. Here it is, and this is a much younger version of me, okay? Notice the date, the Sunday paper, January 26, 1997. And then people started calling me up. You know, Itch Jones, who was coach of the Illini baseball team, he called me up. He wanted to meet and talk about these. Rotary clubs, alumni associations. So for the next year and a half, I was just giving talks, mostly about things I learned by reading Adair's book. And then fast forward to fall semester 1998 when I had a sabbatical, I decided I was going to actually spend some of the time on my sabbatical doing real research in the topic. And out of which grew lots and lots of stuff, and here I am now still doing it. But I have to say I owe it all to the News Gazette, so thank you, News Gazette. Okay. All right, so let's go on. I want to talk about the ball-bat collision first. So here is a really nifty high-speed video. This is at 30,000 frames per second, and the ball is going at 120 miles an hour. It's bouncing off a steel plate. Now, and this is another News Gazette exclusive here. This is Robin Schultz, who's a photographer for the News Gazette, captured this. This is a Central, I don't know which school it is, game from a bunch of years ago. Notice the bat and ball are in contact. This is a real photo of opportunity. And notice that that ball gets crushed. It's flattened out. You can see the same thing here. So that's the first thing to note. When the ball and bat meet, most of that energy goes into compressing that ball. It really gets squished, okay? Second thing to note is that if you look at how fast the ball is going in, notice that it slows down considerably on the way out. It's only going about half as fast on the way out. So a lot of energy gets dissipated. It's a very, very inefficient process. You know, if you were to cut open a baseball, what would you find? A lot of yarn, okay? Wool yarn. Once you take the leather cover off. And when that ball gets squished, the fibers of the yarn are rubbing together, creating a lot of friction, a lot of heat, and that represents energy dissipation, energy that got taken out of the energy of motion of the ball and converted into heat, pretty much useless energy. So that's the other thing to note. The ball gets crushed, and it's a very, very inefficient process. The collision time is very, very fast, so for the ball to turn around and go in the opposite direction in a thousandth of a second requires that, so that's a big acceleration, which requires, therefore, big forces. So the instantaneous forces are thousands of pounds, 8, 9, 10,000 pounds. So that's huge. Okay, now, the only formula you're going to see in this talk is coming up. Right here, this is my only formula. What determines exit velocity? So exit velocity, so in the lingo of the game these days, people talk about exit velocity. I used to talk about batted ball speed, but you watch games on television, they're talking about exit velocity now. It's the speed of the ball coming off the bat. Now, the speed of the ball coming off the bat is certainly an important feature of the ball-bat collision because if you want to hit a home run, for sure you want that to be a high speed. But even if you're just trying to punch the ball through the infield, the higher the speed, the better. So it's a fair question to ask, what does that exit velocity depend on? And so it depends generically on three different things. The speed of the pitch, the speed of the bat, so the bat is being swung, so it depends on the speed of the bat, and it depends on this thing Q here that I call the collision efficiency. It's, in effect, it's a fudge factor that has all the other things that the exit velocity could depend on all lumped in together, okay? Now, typical numbers for a wood bat. Q is about 0.2. That's a small number, okay? If the bat were infinitely massive and the baseball were a Super Bowl, that Q would be 1, okay? But it's not. It's only 0.2. So that's another indication that the collision is very, very inefficient. The other thing to know, and this is rather cute, notice there's a Q here and there's a 1 plus Q there. It's the same Q. Why is that 1 there? The reason why, and that 1 plays an important role. The reason why that 1 is there is because the bat is already moving in the direction that the outgoing ball is moving. That's the only reason why that 1 is there. But it plays an important role because you see 0.2 is multiplying the pitch, 1.2 is multiplying the bat speed. So typical numbers may be 85 miles an hour for the pitch. You say, that's too low for a typical fastball. But remember, it's the speed of the ball as it makes contact with the bat, which is lost about 7 or 8 or 9 miles an hour by the time it got to home plate. Maybe a bat speed of 70 miles an hour, put those numbers in and you get 101 miles an hour. And if that ball is hit at maybe a 30-degree angle, I'll go into more about that later, that ball will carry, around 400 feet, which would be a typical kind of home run, okay? But the important thing to note here is that the bat speed matters much, not only a little bit more, a lot more than the pitch speed in determining the exit velocity of the ball, okay? So each mile per hour of bat speed is worth on a typical fly ball at on a home run type trajectory is worth maybe another 6 feet, whereas each mile per hour's pitch speed is worth only about 1 foot. So really there's a huge asymmetry there. A lot of people don't realize it, but if you think about it, you really knew that already, all right? So imagine trying to bunt the ball where there's no bat speed, yet the ball's not gonna go very far. Now imagine hitting a ball off a tee where there's no pitch speed, you can still hit that ball a long ways. So you sort of knew this already, you may not have known it quantitatively though. Okay, all right, so now, given that I've lumped all this stuff together in this collision efficiency, what does that collision efficiency depend on? Well, it depends basically on 2 different things. It depends on the bounciness of the ball, and it depends on the weight, or maybe more technically correct, the weight distribution of the bat. So let me just quickly here, if I bounce this Super Bowl, so this Super Bowl is pretty bouncy. It comes up to pretty much the same height. So in the technical lingo, it's got a coefficient of restitution, which is close to 1. But look at a baseball. I drop this, and it barely bounces at all. So again, that's another indication of the inefficiency of the collision. Now, and it comes entirely from the ball because of the compression of the ball and the rubbing of the yarn and all that, okay? So the larger this coefficient of restitution, the larger Q will be. The weight distribution of the bat, and by that I mean what really matters most is the weight of, how much mass there is in the vicinity of the actual collision itself. Weight down here doesn't do any good whatsoever. It's really up here. And I'll show you, I have some interesting evidence of that I'll show you shortly. Okay, momentum is conserved, just like the man said, okay? And so you can see that here. Here is the guy bunting the ball, and notice the bat recoiling backwards, okay? And that's a consequence of momentum conservation. So The bat transfers momentum to the ball, turning it around into that direction, okay? And the ball has to exert an equal and opposite force on the bat, forcing it back that way. So if you're bunting the ball, you can easily see that. The other thing you can do is swing the bat, which is the normal thing you're doing, okay? And there, the momentum transferred from ball to bat is not enough to make the bat recoil back, but it does slow down considerably. So this is a softball being hit, the slow pitch softball, and these markers here are being tracked optically. And notice the distance between these markers. The closer they are together, the slower the bat is going. It travels less distance in a given amount of time. So notice right after the collision, the bat slows down a lot. One of my favorite things to do when I'm watching a game that I don't care about, meaning a game in which the Red Sox are not playing, is to listen to the announcers and contradict them, okay? So a few years ago, a couple of years ago, they were talking about Mike Trout, who is probably the MVP in the American League this year, plays for the Angels, and how he is so big and strong that when he hits the ball, the bat doesn't even slow down. And that is complete and total nonsense. It slows down. And if you were to look at high speed, it has to. It is a law of physics. Okay. But it does raise an interesting question. And it's that question that I want to address. So the bat is being held by the batter. And when you talk, so what is momentum? It's the product of mass and velocity, or mass and speed. Okay, well, how much, what mass matters? I mean, if I'm holding this bat like this, I'm left-handed, okay? What about if I hold it, if I grip it really, really tight? Does the mass of my arms matter in this? Okay, what about the mass of the bat down here in the handle? So it's a legitimate question, and you could phrase the question in another way. Suppose you had a big, strong guy like Mike Trout swinging the bat, and you had a scrawny little guy, I won't name names, but you had a scrawny little guy who's obviously not a ball player who managed to swing the bat at the same speed. They made the exact same contact, okay? In which case would the ball travel farther? In the case of the big strong guy, in the case of the scrawny guy, or it simply doesn't matter. All right, so the question is, how much does the batter's grip matter in that ball-bat collision? That's the question. Is there less recoil with a tighter grip? Does the ball leave the bat faster with a tighter grip? Does the batter muscle the ball? That's another thing that announcers like to talk about. Okay, so that's the question I want to address. And there are two key points to talk about here that really get to the heart of the matter. The first key point is that despite the fact that this bat looks pretty rigid and solid, it's not a rigid body. It can vibrate. I'll show you some examples of that. That's point number one. Point number two, the ball-bat collision is very, very fast. We've already talked about that in like a thousandth of a second or maybe even slightly less. Okay, so the bat is not rigid, it can vibrate. So here's some examples. I'll show you them all at once. So here is a bat being hit, the ball being hit on the sweet spot of the bat, and you see the bat slowing down if you're careful looking at it. Now it's hit outside the sweet spot of the bat. I'll tell you what the sweet spot is shortly here. Outside the sweet spot, and notice that bat vibrate. It almost gets knocked out of his hands, and now it's hit inside the sweet spot. So the bat can vibrate, and this little picture here, this little computer rendition, shows you the simplest mode of vibration of a bat. It basically is rotating about, vibrating about two fixed points, one in the handle, maybe 6 inches in, and one in the barrel of the bat, maybe 4, 5, 6 inches in from the end. And it's vibrating about those 2 points. And depending on whether the ball hits outside of this point here, or inside of this point, okay, will determine which way the bat bends initially, okay? So you can see that here. Look at what happens when bats break. So the vibrations can be, if you've ever played the game, you know, if you don't hit the ball on the sweet spot, it stings. That's the vibrations you're feeling in your hand. And if the vibrations are strong enough, the bat could even break. So here is an example where the ball is hit outside of this point here. This is called a node. It's a point that's sort of fixed when the bat is vibrating. And notice that it cracks towards the pitcher. Exactly what you'd expect based on this blue picture here. In this case, the bat is hit inside of this node, and it cracks towards the catcher. So, when I'm watching a game on TV, again, when these guys aren't playing, I sort of look for these kinds of things. Okay, now watch this. So this is a very flexible bat, and that's my hand there hitting it. And here's what I want you to take note of. I'm striking the ball, this ball here on a stick is striking the end of the bat. And what I want you to notice is, look at the motion of the handle. That motion of the handle begins with a noticeable delay after the bat is initially struck. So what's happening is a little wave is created here. You can't easily see it. And that little wave propagates up to the handle of the bat. It bounces off whatever there, comes back down again, and you get this wave going back and forth. Okay? So the handle starts, so this is a result of the non-rigid nature of the bat. By the time the reflected wave gets back down to the impact point, the ball-bat collision is so fast that the ball has already left the bat. So obviously nothing that could happen to the bat after the ball has already left the bat could possibly affect the ball. So if you think about it, nothing on the handle end of the bat could possibly matter as far as what happens to the ball. Not the knob, not the handle, not the grip. The batter could just as well let go of the bat just prior to impact, and it would not make any difference what happens to the ball. Okay? Now you're supposed to say, oh, how could that possibly be the case? Memorial Day weekend, 2012. Todd Frazier, who at the time was playing for the Cincinnati Reds, hit a virtually no-hands home run. So notice, at the time of impact, the top hand is completely off the bat. The bottom hand is very, very loosely touching the bat and lets go pretty much immediately. That ball traveled something like 380 feet for a home run, okay? Thereby confirming that you could just drop the bat as long as just before contact. So the batter doesn't muscle the ball. The grip doesn't matter. And so here are the answers to the question: no, no, and no. Okay. All right. So much for wood bats. Once you learn about bats, then bat manufacturers, they're also calling you up and wanting to talk with you. But I never really worked with a bat manufacturer. However, I did work with the NCAA and more recently the umbrella organization known as USA Baseball on regulating the performance of non-wood bats. Actually, you referred to that in your introduction. And so outside of professional baseball, whether it's major or minor league baseball, most players are using non-wood bats. Back in the day, it was mainly aluminum, but now they're using composite materials, carbon fibers, and such things as that. Why is that better? Now, so here is an aluminum bat. This is a softball bat, courtesy of Rawlings, okay? And this is actually a composite bat. I mean, it's a softball bat. It's got a very uniform barrel. Now, the key thing to know about a non-wood bat is that whereas a wood bat is a solid piece of wood, a non-wood bat is hollow, and that plays a key role. Now, with a hollow bat, with a solid bat, a much larger fraction of the total weight of the bat is in the barrel of the bat than in a non-wood bat, just because this is a thin shell. It maybe is 1/10 of an inch thick. And so the collision efficiency is going to be, the collision efficiency is going to be lower because there's less mass behind that collision. On the other hand, a batter can swing the bat faster because, for the same reason, there's less weight in the barrel of the bat. He can swing that bat faster. And that is sort of a net wash, okay? That is not why the aluminum bat is better. It's basically a net wash. So why is the aluminum bat better? This cup has the answer. It's called the trampoline effect. And it's because when the bat hits the ball, when the bat hits when the ball hits a wood bat, pretty much all of the energy, technically the center of mass energy, but okay, all the energy goes into compressing that ball, which is, we found out, a very, very inefficient process. A lot of energy gets lost. But when the ball hits a hollow bat, the wall of that bat can flex, creating a vibrational mode much like this. And for reasons that are very, very interesting from a physics point of view, but I don't want to go into here now because it's too technical, most of the energy that gets stored up when that bat compresses like this actually returns back to the ball again. So the net result is there's, in effect, a higher coefficient of restitution, a bigger bounce. Why is it called the trampoline effect? Well, you can imagine, you bounce off a rigid floor, you're not bouncing very high, you bounce off a trampoline which can flex, you can get a big bounce, okay? And, quiz time. This trampoline effect shows up not only in baseball and softball, but also in tennis, in golf clubs, okay? A golf driver, you know, it's not your grandfather's driver, which was made out of wood. It's made out of some kind of metal with a thin, it's a hollow metal with a thin plate, and that thin plate can flex just like the wall of an aluminum bat. All right, so here's the quiz. If you're serving in tennis and you want to get a higher speed on the serve, do you want to tighten the strings, loosen the strings, or the strings don't matter? So let me just take a poll. Tighten the strings. Loosen the strings. Strings don't matter. Okay, we'll get to the answer. Okay, so this is that mode that I just described to you, okay? And there's the picture here. So actually now, now comes my little demo table. So what I want you to do is watch the right screen here, the right or left screens. And you can't see this, maybe, but right here I have my surrogate wood bat. It's just a chunk of wood, a cylindrical chunk of wood. And then I also have my aluminum bat, which is a Dr. Pepper can, okay? Perfectly legitimate aluminum bat. It's made out of aluminum. It's got a thin wall, okay? So here's what I want you to watch. So I have a ball here, the two identical balls. I'm going to release them. So the one on the far side, the one furthest away from you, is the wood, and the aluminum is on the near side. You see it? Should I do it again? I'm not watching, so I can't see if you can see it. Yeah, so there you have it. Okay, and so what's going on here? When the ball hits the solid chunk of wood, the ball doesn't bounce at all. It's a totally dead ball. But when it hits that thin aluminum wall, that wall can flex and you get a pretty good bounce out of it. That's what's known as the trampoline effect, and you end up getting an enhanced coefficient of restitution and therefore a higher exit velocity, and that's why an aluminum bat is better. Demo, so you saw the demo. So what's the answer? The answer is you loosen the strings because it's the strings on a tennis racket which is providing the flexible surface to bounce off from. A lot of people would think that you tighten those strings up. Man, I'm going to really hit this hard. But no, you actually want to loosen the strings. Up to a point, of course. You can't have them flopping around. All right, building a worse mousetrap. So here is the NCAA trends, home runs per game, starting in 1970 when aluminum bats were first introduced. They were introduced initially sort of as a cost-saving measure because aluminum bats don't break. And then they learned about the trampoline effect, and they learned that by making that wall thinner and thinner and thinner, you could get a bigger bounce, okay? And they developed all kinds of special alloys of aluminum to allow them to do that, eventually developed composite materials to do that. And anyway, so there were various attempts to regulate here and here. You see there's a drop. But this is the way things stood through the 2010 season, okay? And then a new rule was put in effect based on research done partly by me and others on our team to regulate the performance based on this, basically based on this trampoline effect. What we did was regulate the trampoline effect. And so this is, so you could, the ball bat coefficient of restitution, the coefficient of restitution when the ball hits an actual bat can actually be measured. So you shoot the ball out of a cannon onto a stationary bat. It passes through these light gates, bounces off the bat and bounces back again. And you could measure the speed of the ball coming in, the speed of the ball coming out, and go through a little algebra and come up with this coefficient of restitution. And that's what is done these days to measure the performance of bats. And there is a limit that the NCAA and also the high schools are using, that the ball bat coefficient of restitution shall be no more than some given value, which is a little bit higher than it is for wood, but only a little bit. And what the result of that was, boing, home runs dropped by more than a factor of 2, showing that science really does work. Okay. Lessons for the day. Okay. All right. Switching gears. The other major topic that I've looked at over the years is the flight of the baseball, and this is something that is still ongoing. I think the whole thing with ball-bat collision, all that stuff I just got done telling you is by now fairly old stuff. Useful, but old. This is old, but it's still ongoing. There's still a lot of things we don't know. So here's a picture. We have the ball flying through the air. It experiences 3 forces. Gravity is pulling it down. Air drag, so here are some words here. Air drag acts opposite to the direction of the velocity of the ball. It's slowing the ball down. It plays an important role in the flight of a ball, very important role. And then if the ball is spinning, there is a so-called Magnus force, okay? It's the force that makes the ball swerve from its initial direction. It makes a curveball curve, but it makes, it deflects the ball from a straight line. Both the drag and the Magnus force depend on the air density, okay? So, one way to think about the drag is the ball's going through the air, it's got to push air molecules out of the way. The baseball is pushing air molecules out of the way. And now you can ask yourself, when was the last time you heard baseball and air molecules used in the same sentence, okay? All right? Not so often. So it's colliding with air molecules and it slows the ball down. And so one way to remember which way the ball curves as a result of the spin of the ball is you look at the leading edge of the ball right here, and the ball swerves in the direction that leading edge of the ball is turning. So a ball with backspin mainly swerves up, top spin goes down. I've got some examples here. Here's some really nifty examples. This is just from last weekend. The Red Sox are playing the Rays. And this is Tyler Glasnow. If you look carefully, you can see that the ball that starts out on the left here has top spin. The one on the right has backspin. So for a ball with top spin, it's coming towards you. The leading edge of the ball is going down, so it drops. That's the major thing that a curveball does, by the way. A fastball mostly has backspin, so the force is up, which results in the ball not falling as much as it would if it were under the influence of just gravity alone. Here's another, I love this example. So this is Kevin Cash, who at the time he's now the manager of the Rays, but at the time he was a catcher being used in some emergency role as a third baseman, not a very experienced third baseman. So what happens is the following. So this will just cycle through here. So I'm the catcher here, you're the pitcher. The ball is hit straight up, almost straight up, with a lot of backspin on it. So on its way up, the leading edge of the ball here is going back that way towards the catcher. And now it's coming down, still spinning the same way, but now the leading edge is going that way, okay? And so you can end up with these funny trajectories that initially start out moving away from the fielder, and then as they're falling, start going towards the fielder. And that's exactly what happened here. You can see he overran the ball, and you can see from the way the ball bounced that it had a lot of backspin on it, okay? And I was teaching a class way back, and I mentioned this, and I was told there was a former high school catcher who was in the class, and he told me catchers are all the time taught on a foul pop-up behind home plate, don't commit to what you're going to do until the ball starts to go down, because you might overrun the ball. And you see this a lot. If you watch a game, you see infielders that are under the ball, and then at the last minute they have to back up. It's a pretty common thing to see. Okay, so one of the things I like to talk about is Physics 101 versus real life. So this is a famous home run. This is the home run that Barry Bonds hit to break the all-time home run record in 2007. This shows the actual trajectory of the home run that was measured. Don't ask me how, I won't go into it. But it hit in the stands at this point here, and it extrapolates to about 440 feet or so. So once you have that trajectory, you can create a model for that trajectory, including both the Magnus force and the drag force. And then you can say, all right, since I've got a computer model, I can just turn off the drag force, turn off the Magnus force. And if you were to do that, this is what you would get. That ball would have traveled close to 700 feet. So when they tell you in introductory physics courses to ignore the aerodynamic forces when calculating a trajectory, it works for a lot of things, but it certainly does not work for a baseball. So the drag force, so if you keep the drag on but just turn off the Magnus force due to the backspin on the ball, then you see that backspin, the effect of the backspin is really to oppose gravity. So the ball stays in the air longer so it could go further, at least under the right conditions. So by keeping the drag on but turning off the Magnus force, you lose about 40 or 50 feet or so, okay? So the bottom line being that drag matters a lot. The Magnus force matters also, but maybe not quite as much. And I'll have a little bit more to say about that. StatCast, a new tool, and it's actually not so new anymore. I should have taken out the word new, for doing baseball analytics and physics. So if you go to Busch Stadium, right here is behind home plate. There is this thing that looks like a big widescreen TV. It's black. That's this Doppler radar system that's used for tracking the baseball. So it tracks the baseball, whether it's a pitch ball or a batted ball. It pretty much gets the full trajectory of both pitch and batted balls. When you're watching TV and they show you where the location of the pitch is and the speed of the pitch, this is where it comes from, okay? It's not like the radar gun, the handheld radar guns. It really does come from that. And much of the data that StatCast produces on trajectories of both pitched and batted balls is available completely free online. You can download it. Much of it, but not all of it. And if you've got connections, you can get all of it. All right, so I have connections, so I got a lot more. So I did this study a few years ago. I wanted to look, so one of the things I just skipped over a little bit quickly is that the drag and the Magnus force, they're both aerodynamic forces, and they depend on the density of the air, okay? So the density of the air depends on elevation. There's lower density in Denver than there is here. Depends on temperature, lower density at high temperature, higher density at low temperature, pressure, a little bit on humidity. So here's an analysis that I did based on actual data now. This is real data. So what I'm doing is I'm looking at actual data, Physics 101 versus reality. So here is for exit speeds in the range 101 to 105 miles an hour. So those are typical home run type things. This is the dependence of the distance on the launch angle, okay? So that's another buzzword that you hear on TV a lot, the launch angle. It's the elevation angle of the ball. In Physics 101, the optimum launch angle is 45 degrees. In real life, it's more like 25 to 30 degrees, as you can see here. The second thing to see is this is Denver in red, and this is everywhere else. The Denver effect, where the air density is about 80% of what it, 82% of sea level, it's a huge effect. It's 25, 30 feet, okay? You could see that either by looking at how the distance depends on launch angle for a given exit velocity, or how the distance depends on exit velocity for a given launch angle. And so I've actually showed you this number before. The slope of this is about 5 or 6 feet per mile per hour. Each additional mile per hour of exit velocity gives you about somewhere between 5 and 6 feet. A little bit different in Denver, but okay, anyway. And again, you can see the gap between sea level and everywhere else. So Denver is very, very well known to be a pitcher's nightmare and a hitter's paradise. Not only does the ball carry further, but breaking pitches, for the same reason, don't break as much, okay? So pitches are not as effective, and fly balls travel much, much further. Okay. All right, so the optimum launch angle is 28 degrees. And notice that the distance depends more or less linearly on exit velocity, whereas in Physics 101, it depends quadratically. That's an interesting thing. And again, that's the effective air drag. And the Denver effective shoots. Okay, so what have we learned? By doing kinds of studies like this, we've learned quite a bit. I'm just going to summarize the things that we've learned. Okay, so each mile, the effective exit velocity, each mile per hour gives you about 5 extra feet in distance for something hit at 25 to 30, the optimum launch angle, and that 5 extra feet increases your probability of hitting a home run by something like 15%. That's huge, right? You wouldn't have thought that that little extra distance would matter. But remember, a home run is sort of a binary event. It either makes it over the fence or it doesn't. And if you look at the distribution of fly ball distances, they're dropping rapidly once you get up above 380 feet. So a little bit of change, can result in pushing a big chunk of batted balls over the threshold. Or another way of saying that, for every home run that you see many, many more near misses. And anyway, so next, effective temperature, 10 degrees Fahrenheit. So 10 degrees higher temperature gives you lower air density, the ball carries further. 10 degrees is worth about 3 1/3 feet of extra carry, which is about a 10% increase in the probability of home run. This issue came up a couple of years ago when the Dodgers were in the World Series, and the first, I don't remember which games it was, but they were playing Houston, and the temperature was in the 90s or high 90s, mid 90s, something like that, wasn't it, Tim? So reporters called me up and say, what's the effect? All right, there it is. Effective altitude, each 1,000 feet is worth about 6 feet of carry, which increases the home run probability by 18%. Again, all other things equal, the fence distances and all that. What else have we learned? Assuming no wind, the ball carries better to center field than it does going down the line, even though and that's probably the principal reason why the distance to the fence in center field is longer than down the line. And it has to do with the effect of backspin versus side spin. So balls hit down the line tend to have side spin, predominantly side spin, whereas balls hit the center field tend to have backspin. Effective wind plays a huge role. A small wind, 5 mile per hour wind, can change things by about 18 feet. Now this is a little bit detailed, sorry, but you might think that more backspin on the ball is going to give you a greater distance for the reason that I said already. That is, the Magnus force is up, it opposes gravity, which is pulling it down, so the ball stays in the air longer so it can travel further. And that's true, there is more lift, which generally gives you a greater distance. But it's only been in recent years, the last 2 or 3 years, that we've realized that increasing the spin on the ball also increases the air drag on the ball. And at some point, it becomes the point of diminishing returns. And again, here is actual StatCast data. Distance under certain conditions versus spin rate, you see it rises initially, and then it flattens out, and then it starts to get smaller, okay? So that additional spin, once you're above a couple thousand RPM of backspin, it not only doesn't help, if you start going too high, it actually hurts. Now, golfers know that. For balls that actually, with golf balls, you can get a lot of spin on the ball, and the effect of gravity is a lot less because it doesn't weigh as much. So you can get that ball really going high. And when it really goes high, you can get the ball kind of going sort of straight up, and that doesn't help your distance at all, okay? So golfers know that they need to keep that ball low and limit the amount of backspin on the ball. Anyway, this has very practical implications because a lot of coaches are teaching their players that they should alter their swing in such a way as to get more backspin. And you can question whether that's a good idea or not. At least I do. Now, some actual Major League ball players know my work. Cole Figueroa, who used to play for the Pirates, and now he's a coach or I think he's an analyst for the Tampa Bay Rays, was talking about this very point, about swinging down on the ball as a way to get more backspin and why that's a bad idea. Those of you who like to play around with looking at trajectories can go to my website and do that. All right, so I want to talk very briefly about the spin of a batted ball, and then I want to move on and talk about home runs. So here's a couple of slides here. You can forget about this. Here's a ball being fired in with no spin. It bounces off a cylinder. Actually, it's that very same cylinder that I used over there. And you see it bounces up, and it's got a lot of backspin. And it's the frictional force between the surface of the ball and the surface of the bat that's creating the backspin, okay? Without friction, there would be no spin. So the friction plays a big role. And you see a similar thing here. But I want to show you some examples. So here is what players called a squared-up collision, meaning the ball and the bat are, at contact, the bat is moving right through the direction of the bat is going right through the center of the ball. It's a squared-up collision, and you see the ball's coming off the bat with not very much spin. Here's a case where the bat is hit above the ball, and it creates topspin. And here, this is an example of a backspin pop-up where it's the other way around. You see the ball is spinning with a lot of topspin on it. Okay. Balls hit down the line, I told you already, have a lot of side spin on it. And again, here's an example. You just watch a game and you see this a lot, that balls tend to curve towards the foul pole, okay, whether it's hit to the pull field or the opposite field. And again, it's the friction between the ball and bat. This time not due to the curved surface of the bat, but just due to the fact that the orientation of the bat at impact has a component of the velocity that is along the surface of the ball as opposed to directly into the center of the ball. I'm going to skip this because I want to talk about the home run series. All right. Okay, so here is home runs in Major League Baseball starting with the year 2000. It was on very much a downward trend, and then reaching a low point in 2014. And then beginning in 2015, there's almost a constant upturn. And with the exception of last year, in which it turned back down again. And this year, I did this a couple of weeks ago, this slide. The projection was that there would be 50 home runs by the end of the season, which happens tomorrow. And I'll check to see whether the projection is right or not. But already, the all-time record for home runs was broken a couple of weeks ago, and it's going higher still. Okay? And the question is why? So MLB. Let me go back just for a second. I'm going to talk about the research that we did looking at this increase here. There's currently work going on looking at the increase this year that I'm not going to talk about, okay, because it's ongoing. All right, so having said that, MLB put together a research committee. These are the people. I don't know if you know any of these people, but okay, here are the people. And there were several liaisons. Reed McPhail. Anyone who knows baseball knows the name McPhail, right? This is the fourth generation, I think, of McPhails. He's a young guy that has a job in baseball. Okay, so the ground rules for this were that the committee worked pretty much independently, but we asked MLB for whatever resources that we needed, full access to the StatCast data, not just the publicly available data, baseballs for doing laboratory testing to measure things like drag coefficients and stuff, and coefficients of restitution, test data from Rawlings, the company that makes the baseballs. We visited the manufacturing facility, more on that in a second. We set our own agenda, arrived at our own conclusions, and wrote out a report, and you could read that report right here, okay? So, so what's next? Oh yeah, visiting the facility. It's in this place called Torrealba, Costa Rica. So you fly from Atlanta to San Jose, and then you take a long ride in a van, 2 hours through lots of traffic. And all right, anyway, to get to Torrealba, which is one of the biggest employers in the country. And so we had a nice tour, and this is an amazing thing here. You know, the ball, if you open up a ball, as I said, it's mostly yarn, but at the very middle, there's this thing called the pill. It's a little rubbery thing. And then there's the yarn, and the machines wind the yarn, and we weren't allowed to take pictures of that. But we were allowed to take the pictures of the room full of people that are all day long sewing the seams, okay? So there is a leather cover and, you know, 2 pieces of leather that have to be sewn together, and that's what they're doing here. Okay? So a lot of the construction of the baseball is done by machine. This part is for sure done by hand. And here's a bit of a close-up there. You know, the ball is made and they're fixing the seams, and a lot of the judgment as to whether it's an acceptable ball or not is just by eyeballing it. Okay, anyway, that was kind of interesting. So let me just talk about the possible reasons why there might be a change in home runs, and then what we concluded, and then where we're going next. Okay, so there are 2 generic reasons. One reason is a change in the launch conditions themselves. Higher exit velocity, more optimum launch angle. So one way you could have a higher exit velocity is if the ball is juiced in the meaning that people used to attach to a juiced baseball, meaning that coefficient of restitution is higher, it's more bouncy. That'll give you a higher exit velocity, which will give you more home runs. Or maybe the batters are just swinging harder, okay? More optimum launch angle. So if you hit the ball really, really hard at, 0 degrees, you might get a single, but you're not going to get a home run. You got to get the ball up, 20 to 35 degrees in that range there. And people talk about the launch angle revolution, that batters are purposely altering their swings in order to achieve not only high exit velocity, but also a more optimum launch angle for hitting home runs. So that's the first generic reason, change in launch conditions. The second generic reason is the ball is carrying further. So for given launch conditions, exit velocity, launch angle, spray angle, spin, the ball is simply carrying farther due to reduced air drag. And so what did we find? We found you could not account for the change in home runs between 2015 and 17 by a change in launch conditions. Instead, it was due virtually entirely to a change in the way that ball carries. Okay? So that's the answer, at least for 2015 to 17. How do we know? We can go into lots of discussion about how we know, but let me just say that we had all the StatCast data. We can look at distributions of exit velocities and launch angles. We can look at actual trajectories of balls as measured by the StatCast system, both for pitch balls and batted balls. We did laboratory measurements of both the coefficient of restitution of the ball, as well as the drag and the lift on the ball. And then, and this is where I came in, you could develop a physics model to see how any changes in any of those things would result in a change in home runs. And we came up with a very, very consistent picture that it really was a change in the carry of the ball, not a change in the launch conditions. And, okay, I'll skip that. But now there was good news and bad news. We know that reduced drag accounts for the increase in home runs. That we knew. But we could not, try as we might, find what physical property of the baseball resulted in a reduced air drag on the ball. We looked at things like the height of the seams. We looked at the texture of the surface of the ball. It almost has to be a surface effect because when the ball goes through the air, the only thing that the air knows about is is the surface of the ball. And probably it's going to end up being something associated with the seams. That's the most likely thing. But we really, as of our report from a year ago, we don't know that yet. But so suffice it to say that home runs were down in 2018, as I showed you already. They're back up in 2019, and we're hard at work on this. And I'm not going to say anything else about that. Okay. All right, so look, I'm done. Lots of examples of how physics enters the game of baseball, and I've really only covered a little bit of it here. Feel free to contact me. I love talking about this. Follow me on Twitter. My Twitter feed is virtually no politics. It's only baseball. And that's me in my uniform at the Red Sox fantasy camp back 10 years ago. I mean, you put a uniform on, everyone looks like a ball player, really. And thank you.
All right, thanks, Professor Mason, for a fantastic talk. I'll take some questions now. Yeah.
Could you hollow out a wooden bat like some players in the past have done? You also get the trampoline effect.
So
Okay,
let me just repeat the question.
Yeah, I'll repeat the question. So the question is, if you take a wood bat and do what is known as corking the bat, you drill out a hole here. Sammy Sosa did this, right? And does it create because now you've got at least a partially hollow bat, does it create a trampoline effect? Quick answer, no. I mean, it's not obvious that the answer is no, but no, you could measure and show that it's no, and we did such measurements right around the time Sammy Sosa did this. I mean, the hole that you drill is like an inch in diameter, maybe 12 inches deep, and that still can't flex very much when you do that. So the answer is no.
You have a bat in your hand. Why ash?
I don't know if I have a good answer for that. Ash used to be, maybe not so much anymore, quite plentiful. You're looking for something that is hard, okay, that is rugged, so it won't break as easily, but yet it has to have a fairly low density because you have to be able to swing the thing. And back in the old days, they used to use hickory, which is actually a bit more dense than ash. Nowadays, over half the bats used in Major League Baseball are maple, and that's a trend that continues. And I think part of the reason for the trend in maple is that when Barry Bonds set the single-season home run record, he was virtually alone in Major League Baseball in using a maple bat, and everyone just wanted to copy him. There have been very, very careful measurements done that show that maple is certainly no better than ash in performance. But it is true that the ash trees are dying off, and so I think the trend towards maple is probably going to continue. Yeah?
Do changes in weather conditions affect drag?
Oh, absolutely. So yes, temperature, if the temperature's higher, the ball's going to carry further. And so you have to correct for that. I mean, when you're doing the kind of analyses that I talked about, you have to correct for that. So you can get weather information. That's very, very easy, with one exception. The difficult thing to take into account is wind. Because the wind in four-dimensional space, x, y, z, and time, is not constant. So you look at a stadium and you see you look at the flags and you see they're going in different directions at different places in the stadium. It's not the same now as it was 2 minutes ago. And so it's very, very hard. And it's very much influenced by the local, by the structures in the stadium itself. Okay, so getting wind speed and direction from the nearest airport is really maybe indicative a little bit, but it's not quantitatively speaking very helpful. So it's very hard to do that. That home runs what? Sorry? Oh yeah, for sure. So the question is if a ball carries better at high altitude as it does in Denver, does that mean home runs are more common? Yes, absolutely. And that was realized very early on when the Colorado Rockies first came into existence. And you try to compensate by moving the fences back. But of course, that's trading one problem for another, because when you move the fences back, there's more real estate that the fielders have to cover, so you may get fewer home runs, but you get more balls in the gap for doubles. So yeah, things are tough in Denver if you're a pitcher.
What about the humidor? How does that actually come?
So we asked, what about the humidor? Okay, so that's another thing that they did. So what does the humidor do? So I gave a whole series of talks about humidors. All right, so in Denver, they got the idea that one way to combat the high propensity for home runs was to store the baseball in a humidor. And the idea is this, and Denver is actually very, very dry on a summer night. Relative humidity maybe 30%, something like that. Around here, what is it in St. Louis? 90% or something. And when the ball is stored in a humid environment, it absorbs water, and it gets a little bit more massive. That's a small effect. But it actually reduces the coefficient of restitution. So one of the ideas that they had in Denver was to store the ball in the humidor at 50% relative humidity, 70 degrees, which resulted actually in a 25% reduction in home runs. And that's something that I actually, I made a post-addiction, not a prediction, because it was done before I was involved with all this, but you could pretty well account for where that 25% comes from. More recently in Arizona, at Chase Field, which is even drier, beginning in 2018, they started using the humidor, and that resulted in a reduction in home runs. Maybe somewhere around 30%. It's a bigger reduction because they're going from roughly 20% humidity up to 50%. Okay, so but you could more or less account for these things just by knowing what the coefficient, how the weight of the ball, as well as the coefficient of restitution of the ball, depends on humidity, which you can measure in the laboratory.
Why are home runs so bad?
I have no value judgment as a physicist, but as a baseball fan. So I'll give you my answer as a baseball fan. Guys like Bill James talk about the three true outcomes, okay? Walks, strikeouts, and home runs. So these are three outcomes in which the players on the field outside of the pitcher play no role whatsoever. Okay? A ball goes over the fence, the fielder had no chance to catch it, right? The fraction of plate appearances resulting in one of those three true outcomes has actually gone down in recent years. There are fewer balls in play, and it's not so much the walks. Strikeouts are up, home runs are up. And with fewer balls in play, there's less opportunity for the fielders to make a spectacular play. Now, when I'm watching a ball game, regardless of whether it's my team or the other team, when I see a spectacular fielding play, I'm in awe of that. I love it. Now, some fan, again, I'm talking as a fan now, not as a physicist. So that's what I like to see. But I think that one of the reasons why people ask, as you asked, why are home runs bad, is that baseball is a very conservative game. They're very conscious of records. And I think that fans like to know that a home run hit in 2019 has the same meaning as a home run hit in 1975. That it didn't come as a result of a juiced ball, as people think happens now, or a juiced player, as happened in the 90s, okay, during the steroid era. So again, that's not a physics answer, but it's a baseball fan's answer.
Great. Take two more questions, then you're welcome to talk to Professor Nathan, as long as he's willing to talk to you. Let's say one back there. Yeah.
Has the cricket, there is one guy I know in cricket, and no, the answer is no. No one has asked for my help, and nor have I volunteered it. I have a heck of a time just understanding the game. But there's a lot of similarities, and actually, I think, so look, there are very few people doing research in the physics of baseball. I mean, there might be, I don't know if there's anyone doing what I'm doing, really. Not that they couldn't, but isn't. There are people doing research in the physics of cricket, developing cricket bats, looking at the aerodynamics of a cricket ball going through the air. For whatever reason, there just seems to be that sports science is somehow maybe a more respected occupation in the UK than it is, and in Europe and Asia than it is here.
Did you do any research with the effect of the pitching speed? Not the speed, but the spin on the ball. Like would a knuckleball have any particular effect opposed to those the underspin and the overspin you had an example of?
Yeah, so the question is, so let me just state the question maybe generically. What effect does the spin of a pitch have on the batted ball? And knuckleballs, of course, are thrown with very, very little spin. The quick answer is that the way it's likely, certainly it has an effect on the location of the pitch, how much the pitch moves, and that certainly affects the batter's ability to hit the pitch, especially if the batter is fooled on it and whatever. But if a different question to ask is, what effect does the spin of a pitch have on the spin of a batted ball? And the answer is not very much. It mostly comes from what the bat does to the ball, not so much in what the pitch does. But that's sort of it's not obvious that that's what the answer is. It's one of these things that it quotes, it just turns out that way. There's no fundamental reason why that has to be the case.
All right, so let's thank Professor Nathan again.